So this is the 2018 probability external for level 2, standard 91267. So this was sat yesterday at the time of recording this, which means the mark scheme is not available yet, and this is just my best attempt at the paper, and the mark scheme might come out a little differently. I also welcome any corrections. If I make mistakes on this, just pop a comment in the bottom and I'll put corrections underneath the video. We will start with question 1a, and we have that we've got some temperatures being recorded. These are daily temperatures and they're recorded at various locations around New Zealand by this organisation with the acronym NIWA. They record that daily temperature by finding the mean of all the recorded temperatures in this 1 24-hour period at the various locations around New Zealand. So over the last 7 years, the daily temperatures in Reefton, so this is the location that we're looking at, have been found to be approximately normally distributed. The mean is 11.6 and the standard deviation is 4.8. We're going to work out what's the probability that a randomly chosen day in Reefton would be between 11.6 and 18.8. So the first thing that we need to do is draw a diagram. So we've got a normal curve. The mean is 11.6 and the standard deviation is 4.8, and we are working out the probability between 11.6, so that's right on the mean, and 18.8. We want to work out this area here. You can read that off the table or you can put it into your graphics calculator. I'm going to choose the second option. Graphics calculator is a lot faster and easier, so when we put that into the graphics calculator, we get the answer where the probability is equal to 0.4332, and in brackets I'm just going to put GC to show that was done on the graphics calculator. Part 2 asks us to find the probability that the temperature is over 17 degrees. We're working with the same normal distribution, so we've got the mean of 11.6 and sigma is 4.8. This time we're looking for it to be over 17, so if there's our 17, we need that proportion represented above the 17. It's really important that you draw the diagrams, especially if you're using the graphics calculator. Part of the beginning of this question said that working in diagrams must be shown. There's not much working to be shown if you're using the graphics calculator, so you must do the diagram. Okay, so pop it into the calculator, and we're going to do a right tail or upper limit of a very high number, and we'll get our probability. It's probably worth writing down what you entered into the calculator to be able to get your answer, and then the probability is 0.1303. Part 3 is an inverse normal question. We're asked to work out the value when we know the probability or percentage. So the hottest 1% of days are scorchers, so there's some value here that defines it as a scorcher if it's in the top 1%. We're going to use inverse normal on the calculator to work that out. And that gives us an answer. If you pop all of those in, you get 22.766, so we'll round that to 22.8 degrees Celsius. So this one, we're told that the temperatures in Reefton increased due to climate change. So that means that the mean is going to get bigger, so mu is going to change here. So it's telling us that mu is going up, but the standard deviation stays the same. And we want to work out what this new mean will be. We're told that the daily temperature for Reefton, if the probability of being lower than 9 degrees falls to 20%. So we need to put that information together on the diagram. So the standard deviation remains the same. The mean we don't know, that's the thing we're going to work out. But we are told that the probability of the temperature being lower than 9 degrees will be 20%. We want to work out what's the mean to make that happen. We need to use our z values for this one. So we need to work out what z value would go here. On the standardized z curve, you have the mean is 0 and the standard deviation is 1. So we can do the inverse normal on the z curve to work that out. Using all that information there I've written in blue. So that gives us a z value of minus 1.340755. Now we match up z with the x value we're looking for, the mean that we're looking for, with this formula where z equals x minus mu over sigma. So z is the minus 1.340755 that we just worked out. X is the value it happens at, which is 9. Mean is what we're trying to work out, so we don't know that yet, and sigma is 4.8. Now use equation solver on your graphics calculator or rearrange that manually and you can work out what the mean is. Which means we get that the mean would need to be 15.44 degrees Celsius to have that probability of being less than 9 degrees come out to 20%. So part B is an interesting question. It's really testing you on understanding what's going on the normal distribution. It's a bit of an unusual one, but it shouldn't be too tricky if you've really understood from the beginning what normal distribution is all about. So it's asking you to show that the interquartile range is always greater than the standard deviation. Now a reminder about the normal curve. So we have the mean in the middle. Now the normal curve by its very definition is set up in such a way that if you go 3 standard deviations away from the mean, you will cover 99% of your data. So if we just draw that onto this picture, then this is what it looks like. But you also need to remember those other values too for this one. So if that's all of the data, what would it be just 1 standard deviation away? So 1 standard deviation on either side, that will always contain 68% of the data, okay? Which means that's across 2 standard deviations, 1 above and 1 below the mean. So 1 standard deviation would cover 34% of the data. However, the interquartile range is from the bottom 25% to the top, to the 75% mark. All right, so it covers 50% of the data. It would be something like this, up from there up to there, 25% on either side. So we can come to the conclusion that since the IQR will always cover 50%, but the standard deviation only covers that 34%, the interquartile range must always be bigger than the standard deviation. I'm not sure exactly how they're going to mark this one. This has got to be an excellence question in my opinion, and I'm not sure how they'll grade the U, R and T portion of that, but we'll see when the mark scheme comes out. Nice simple start to question 2. We've got a table of number of days that were wet or dry or windy or still in Kaitaia. So the proportion of days over this time that were windy, we simply read that off of the table. So we've got windy days out of our total days recorded will be 1646 over 2556. And if you wrote that as a decimal, which probably isn't necessary, it'll be 0.643. Oh no, hold on, the next one rounds up, so 644. So question 2, or part 2, is pretty straightforward. What proportion of wet days over this time were still? So we are restricting this down to only look at the wet days, giving us a total of 641, and of those 88 were still. So it's 88 out of 641, and if you wrote that as a decimal, it would be 0.1373. I'm going to 4 decimal places just to be on the safe side. If you did 3, that's probably fine as well. Part 3 asks us to compare the chances of being wet on a windy or a still day. So let's split those up. So the probability that it's wet given that it is windy, so we are looking at only the windy days, the chance of them being wet is 553 out of 1646. Similarly, if we go for the probability of it being wet given that it's a still day, we'll be looking at just the stills, and that's the chance of them being wet are 88 out of 910. I'm going to change both of those into decimals to make them easier to compare. So now looking at those calculations, we can see there's a much higher probability of it being wet on a windy day, and we write a sentence for that. So simply put, it's more likely to be wet on a windy day than a still day. Now, they haven't asked you to say how much more likely, so I don't think you need to go to the next step of actually calculating that relative risk. But just for completeness here, I'm going to put it in anyway. If we do those, that 0.336 divided by 0.0967, we get that it's 3.47 times more likely to be wet on a windy day than a still one. So part 4 is saying, can we use table 1 to predict what would happen in February of 2019 for this athletics day? So one statistical reason why that table wouldn't work, well, the table was done as an average of, or rather it's totaling up the number of windy and still days and all of that from the last 7 years from all across the whole of the year. So it's averaging out the effects that you would see, and since February is in the summer, you would expect it to actually have better weather than what is represented by that average in the table. So you write something along those lines. Now we've got some tables of the same idea, but we've got the table from Kaitaia and also one from Reefton to compare the different weather in the 2 different places for Matthew and Tamati, his brother. So Matthew claims that it's 20 times more likely to be windy when it's dry in Kaitaia than it is in Reefton, and we're going to compare those 2 probabilities and see if he's right. Okay, so just shrinking that down to just the 2 tables, so I've got space for some working. We want the chance in each of those places and then work out that relative risk. So we'll start with Kaitaia. The chance that it is windy when it's dry, so we're only looking at the dry section. The chance of being windy is 1093 out of 1915 dry days. And then we'll do the same for Reefton, which comes to a probability of 53 days out of 1673 dry days. Now we're going to do the Kaitaia probability divided by the Reefton probability to see how many times more likely that is. And that comes to 18.02. So it's 18 times more likely in Kaitaia than Reefton, not quite the 20 that Matthew claims, so we write a sentence for that. For question 3, we've got some information about Ashburton and Timaru. And before going on to calculate anything, they do give you some space to draw a diagram to set it out, and that's always a good idea, so that's what I'm going to start with. Now the first part of the tree diagram is pretty straightforward. Ashburton's wet or dry is 45% chance of being wet, so 55 of dry. Now if it's wet in Ashburton, the chance that Timaru is also wet is 63%, so that'll be 0.63, making the chance of being dry 0.37. But then if it's dry in Ashburton, the probability that it was also dry in Timaru is 0.88, making the chance that it's wet 0.12. Then the question asks us, find the probability that it was dry in both Ashburton and Timaru. So we want dry on both days is here. So the probability will be equal to 0.55 multiplied by 0.88, which comes to 0.484. Now we want the probability that only one of the towns is wet, so that could be that we have Ashburton wet and Timaru dry, or Ashburton dry and Timaru wet. So we're going to work out the probability of each of those. And then we can satisfy that condition of only one town being wet either one of those two ways, so we add them together. For part 3, I've just copied across the tree diagram again, but this time including the probabilities of each branch at the side, because we've worked out most of them already. And now we want to work out what's the probability that if we know it was a dry day in Timaru, we will also have a dry day in Ashburton. So it's a conditional probability. We're restricting down the branches that we want to look at. So we will only consider like our new total to be for all the days that are dry in Timaru. So that's this section here and this section here. So there. Now we've got a third town being introduced of Waimate. So Nancy's grandfather says that the chance of it being dry in all 3 towns is between 30 and 35%. On the day of the ride, she gets a dry day in both Ashburton and Timaru. Now we already know the chances of that, so Ashburton was 0.55 dry, and then Timaru was 0.88. If I'm just picking out the bottom branch from the tree diagram that we had before, then if Nancy's grandfather is correct, what's the smallest probability that it's wet in Waimate? So we've got the last town in the stop. Now if that was another branch on our tree diagram, her grandfather's statement is that that total probability would come to between 30 and 35%. Now, to get that total probability, we would times across the branches. So there's got to be something here that will multiply to give us that 30 to 35%. So what's the smallest probability that it could be? Now, just be careful here. I've just noticed. Now, Nancy has a friend, Terry, who turns out not to be particularly smart, but anyway, she knows that 45% of days in Ashburton are wet and 35% of days in Timaru are wet. You've also been given this map to see So we need to explain why Terry's tree diagram would not give a correct answer to the probability that we get both of the towns being dry on the same day. So first of all, by looking at that map, we know Ashburton and Timaru are quite close together. So their weather is not likely to be independent of each other. If it's wet in one, it's probably wet in the other one as well, because weather doesn't vary that much when things are close together. And you can even use the scale on the map to measure how much that is. It comes to be approximately 70 kilometres apart using that scale. Now, the way to say this statistically is that the probabilities of wet and dry days in each town are not